This is video 2.6. You should only be watching this if you are considering AP Chem. This is a good introduction to what we're going to get into in electron configurations, but there's a lot of information here that we will not cover in Regents, so it's not something to stress yourself out with. However, this information will help understanding electron configurations a little bit easier and bonding in general that we'll get into later in the year. Okay, so let's get to it. All right, quantum numbers and atomic orbitals. Quantum numbers, guys, they specify the properties of an atomic orbitals and their electrons. Okay, there are 4 quantum numbers that we're going to talk about. Ideally, or essentially, these are telling us where electrons are. Okay, trying to pinpoint as best we can electron location. Okay, we're going to find out that, hey, we can't exactly get it, but we can get in the general area. So the first quantum number is called the principal quantum number. This indicates the energy level, all right, that is that the electrons are on. So the kind of way that we think about it in terms of you know, the traditional idea like Bohr's model, right? These would be the orbits, like in the planetary model. Each orbit is an energy level, so that would be a different principal quantum number. As n increases, so does energy. So the farther out you go, right, the bigger the ring, the more energy that those electrons have. So the number of electrons on a level mean 2n squared. Okay, so if we were asked to figure out how many electrons are just on energy level 2, we would just plug in 2 for n, and we do the math. So 2 squared is 4, times 2 would be 8. So if we figure out, okay, energy level 4, same idea, plug in 4 for n, so 4 squared is 16, times 2 would give us a total of 32 electrons on that energy level. Okay. The second quantum number is called the orbital quantum number. It's traditionally symbolized with the lowercase l. This indicates the shape of an orbital and the subshells or sublevels that are there. We have 4 sublevels on an energy level, that ones that we can actually see. SPDIF is the way that I remember it, SPDF, okay, in that order. So S is filled first, okay, which this should be review, kind of remembering or helping you guys remember it from that POGIL activity that you did to introduce electron configurations. N equals 1, it's got 1 energy level, and that's called 1s. N2 has 2 subshells, 2s and 2p. So if we continue in that same fashion, N equals 3 should have 3 subshells that are named 3s, 3p, and 3d. All right, and continuing on with 4, it's the same pattern: 4s, 4p, 4d, and then 4f would be the last one. Okay, within those subshells, they contain orbitals. All right, and there's a pattern with this as well. P has got, so S has 1 orbital, and each orbital can hold 2 electrons. Again, think back to the bunk analogy. These are the rooms. So you've got, or the bunks that are there. Each bunk can hold 2 people. Those are the 2 electrons. All right, within each room, so like the P is going to be the room. There were 3 bunks, so 3 orbitals. All right, 3 times 2 would be a total of 6 electrons. Continuing along, so 1, 3, D has 5 orbitals, can hold 10 electrons. What do you think F is going to be? 1, 3, 5, 7, it can hold 14 electrons. And this corresponds to the periodic table, which we'll talk about in a future video. Now, the shapes, honestly, the only ones you need to worry about, even for AP, would be the S, and that shape is a sphere. Okay, not a circle, it's a sphere because these are 3-dimensional. And then the P's are a dumbbell shape. All right, kind of like a lazy 8. So it's like this, right? So it's not an 8 that is up, it's an 8 that's on its side. The next quantum number is called the magnetic quantum number. That's symbolized with lowercase m. Really, guys, this is just showing the orientation about the nucleus. So if I were to draw all of the different axes you could have, so you got x, y, and then this last one is the z-axis. All right, so I'd have a P there, so that's around my y-axis. This one would be around my x-axis, and then this last one here would be around my z-axis where it's coming out of the board. So I can try to highlight it. I don't know how good it's going to be. All right, so there's 1, and then there's this guy up here and this guy right there. So those would be like the 6 different orbitals, excuse me, the 3 different orbitals, the 6 different locations on the P. Don't worry so much about this, even for AP, they're kind of moving away from it, but this is what's happening. And then the last quantum number, guys, is called the spin quantum number. And that just shows this spin, okay? So it's either plus a half or minus a half. It's showing us that, hey, it's either clockwise or counterclockwise. We'll talk more about this when we get into our orbital configurations here in a couple videos, okay? The thing you want to remember, so I'm sorry, really quickly, either a positive spin or a negative spin up or down. So it's kind of like, oh, this is spinning this way, and this one is spinning this way. They have opposite spins. You can also see it like this, okay? And we'll talk more about that, like I said, in a future video. Pauli's exclusion principle states that no 2 electrons in an atom can have the same 4 quantum numbers. Okay? Therefore, 2 electrons in the same orbital must have opposite spins. Okay, and this really relates to energy, which we will talk more about in a future video, but that's why. Spinning oppositely is less energy than spinning the same way. So if we talk about the quantum number pyramid, all right, this is kind of saying which is the most broad number and then which is the most accurate, trying to get closer and closer to where the electrons are. So we're going to do an upside down pyramid, something like that. The top level is going to be the principal quantum number. Okay. Then we're going to break up the next one into kind of 2 sections. And this is your quantum number 2. So we have the orbital quantum number, and then which actual subshell, right? Because the orbital quantum number is kind of telling us which one it is. So that would be your SPDIF, right? S, P, D, or F. And then number 3 is going to be the magnetic quantum number, getting closer and closer to where that electron is. And the last one is going to be the spin Q number. Okay? So the analogy that I use here is like, okay, starting at the top, this is kind of like what country you're in. The second one then would be like what county you're in, what city you're in, what street you're on, and then what house you're actually in. Okay, so that's kind of the idea there. So as we get more and more down, you need all 4 quantum numbers to determine where an electron is, or most closely is. But what we'll focus on mostly in this class is really just this principal quantum number. All right, AP will go a little bit deeper with the subshells. But again, the subshells that we will see with the configurations help our understanding of bonding that we will be doing in a later unit. So if we talk about the energy level, what subshells we could have, S, P, D, or F, the number of orbitals that we have in each sublevel, and energy level, and then the maximum number of electrons in each subshell, and then we have our total number of electrons. Again, the formula for that is 2n squared. This is something that's going to be easy to help you, and we may even see that on the regents, which we'll talk about. So, subshells in energy level 1, we have 1s. All right, there's 1 orbital, and it can hold 2 electrons, so we have 2 electrons total there. Energy level 2, we would have 2s and 2p. 2s has 1 orbital, p has 3. So the total number of electrons that we can have in that orbital on the 2s is 2. The total number of electrons we could have on the 2p orbitals would be 6, for a grand total of 8 electrons in that whole entire energy level. So you can kind of see the pattern that starts to form, right? 3s, 3p, 3d, 1, 3, 5, 2, 6, 10. Add them up, we would get 18. And we can continue that here, 4s, 4p, 4d, 4f, 1, 3, 5, 7, 2, 6, 10, 14, for a grand total of 32 electrons. So again, if we take a look at it, right, 2n squared, oh, that gives us 8. All right, so each one of these, yeah, we're adding them up because I've shown that, but this shortcut method to get us to where we want to be makes it a little bit quicker, so we don't have to think about that. Okay? So, again, this was kind of a brief overview of what these quantum numbers are. AP, we would go into them in more detail. So I'll see you guys in the next video.